Hello everyone, today we are learning a lesson about sampling distribution, difference of means. This is very similar to what we have already learned when it comes to sampling distributions, except for distribution of means means that we are looking at numeric data now. So basically we're doing and looking at a lot of things that we already know to be true, but we're just looking at the difference of numeric means now. So let's get into this. Is one form of the AP exam harder? Last year, our high school had 30 students take the AP Stats exam. We were informed later that the College Board gave 2 forms on the exam, which were randomly assigned to the students. Here are the results. Form A got the following scores, and Form B got the following scores. We're supposed to find the mean score for Form A and the mean score for Form B. So how we're going to do that is we're going to put Form A into list 1 of our calculator and run the one variable stats, and then put Form B into list 2 in our calculator and run the one variable stats. So go ahead and pause the video now, get those means, and then when you're ready, unpause. All right, so you should have gotten that the mean score of Form A is 4.2 and the mean score of Form B is 4. What is the difference in the means? And you can see here it tells us to subtract A minus B. That mean difference is going to be 4.2 minus 4, which is 0.2. Okay. It says, assume the 2 forms are the same difficulty. So regardless of the form you get, you're going to score the same, is what this is saying. If Doug scored a 5 on Form A, he would still score a 5 on Form B. So in other words, Doug gets a 5 no matter what form he's assigned. This is something that we would do together in class, similar to what we did with proportions, where we were looking at people yawning or not yawning. We would simulate this together. What we would do is I would give you 30 individual little pieces of paper with the scores on them, etc., etc. We would shuffle them up. We would put 15 scores into one pile representing Form A, 15 scores into another pile representing Form B. We would take the average of those two piles. For example, for Form A, I could get 3.5. For Form B, I could get 4.25, depending on the combination of scores I get. And then I would look at that mean difference, which would be a negative 0.30. I would then put that on the board on the dot plot at negative 0.3. This is what we would do if we were in class together, but since I'm not there today and we are not doing this in class together, what I'm going to do is I'm going to just go ahead and show you a distribution that is a simulation of 21 scores. So go ahead and copy down the distribution dot plot below. Okay, so what we're basically doing is we're pretending that we went ahead and simulated that, and these are those differences that we would have gotten. There's 21 observations here. It says the high school had a difference of mean scores of 4.2 minus 4.0, which is 0.2. Is this outcome surprising if we assume both forms are the same difficulty? Let's look. So what is the likelihood of getting a mean difference of 0.2? Well, out of these 21 simulated observations, what's the probability of being 0.2 or more extreme, which is greater? There are 1, 2, 3, 4, 5, 6, 7, 8 observations out of 21 that are 0.2 or greater. That's 0.38 or 38%. So is this surprising? Well, no, not really. So no, assuming the forms are the same difficulty, there is a 38% probability of getting a difference of sample means of 0.2 or higher purely by chance. because remember, this is something that was simulated, and we still got quite a few scores of 0.2 or higher mean difference. So down here it says, based on the simulation, do we have convincing evidence that one form of the exam is harder than the other? Well, if we compare 0.38 to a standard alpha value of 0.05, this is greater, so we would fail to reject the null, and we would say, like, no, there's not significant evidence against the null. Our initial claim is that they're the same. There's no difference, right? So this result is not surprising. Since, it's more than 5%. We do not have significance of evidence. That one form is more difficult. All right, let's head to the back to get some notes and finish up some examples. All right, so we're going to talk about the sampling distribution for the difference in sample means. So just like with proportions, we can talk about the shape, center, spread. The shape of the distribution, we already know how to look at the shape of a numeric distribution. We know that the shape is approximately normal if one of three options are satisfied. And the only difference is that for the two samples, both of those samples have to satisfy the condition. So approximately normal if both samples meet this criteria. Option 1 is, remember that population is stated as normal. Option 2 is that n sub 1 is greater than or equal to 30 and n sub 2 is greater than or equal to 30. That means by the central limit theorem, they're both approximately normal. And option number 3 is that the normality plots are approximately linear, so the distribution is approximately normal. All right, the center is just like what we learned for one sample. The center of the sampling distribution of the differences of means is equal to the parameters, mu sub 1 minus mu sub 2. And here's our formula for standard deviation for the difference of sampling means. We've got a big square root, sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. All right, so the U-try problem below runs you through these three properties that we learned, the shape, center, and spread. So why don't you take a second to pause the video, go ahead and read the U-try, complete parts A, B, and C, and then unpause the video to check and see how you did. Okay, so going over the U-try, we can see that the shape of the distribution is normal since, if you notice, both the distribution of men and women is stated normal. So part A, easy to do. Part B, we follow that formula right here that the mean of the sampling distribution is equal to the two parameters subtracted. Those are stated above. We see that mu sub m is 69.3 and mu sub w is 64.5, and when we subtract those we get 4.8, so that's the center of the sampling distribution of the differences of means. And then we follow that formula for the standard deviation. You can see above that sigma sub m and sigma sub w are provided. Plug those directly into the formula and get out 1.088. The difference in sampling means typically varies by 1.088 from the true difference in means of 4.8. So Today we just learned the basics of the sampling distribution of means, and when we come back together, we will be going through 2 sample intervals as well as significance tests. So hopefully you see some parallel lines between these things, and I will see you guys soon. Bye.